Good morning. In today's video, I'll be telling you the difference between these two terms, allotropy and polymorphism. Now, allotropy and polymorphism are two closely related terms. Actually, one of them is a subset of the other. Now, it's possible to define them very briefly. We say the existence of two or more forms of an element, a substance in the same physical state. Yeah, now look at this. The existence of two or more forms of an element, so we leave this out for now. The existence of two or more forms of an element in the same physical state, that defines allotropy. Whereas the existence of two or more forms of a substance in the same physical state, that's the definition for polymorphism. Now, in basic chemistry, the word substance can refer to any of the following three things. It could be an element, it could be a compound, and it could be a mixture. All right? So substances can be of these three types. Now, irrespective of the type of substance you have, as long as that substance exists in two or more forms in the same physical state, you say that substance is exhibiting polymorphism. But what if the substance is an element? Yes, it is still polymorphism, but that polymorphism can now be called a special name, which is allotropy. So which means allotropy is polymorphism in elements. Yes, when an element exhibits polymorphism, then we call it allotropy. Now see examples. There is the compound called silica. Silica is SiO2. And this silica exists in three crystalline forms. We call them quartz. We have tridymite. And then we have cristobalite. Now, these three crystalline forms of silica, we refer to them as polymorphs, all right? Because a substance, silica, is existing in two or more forms in the same physical state. But can we also call them allotropes? No, because silica is not an element. Instead, it's a compound. Then what about lead 2 oxide, PbO? That one can exist in two forms. We call them massicot and litharge. Massicot and litharge are two forms of the same substance, precisely a compound in the same physical state. So we say these two things are the polymorphs of lead 2 oxide, just as these three are the polymorphs of silica. But cross over to this side now. Let's say we look at an element like carbon. Carbon can exist in the form of diamond and can also exist in the form of graphite. Based on that, we say diamond and graphite are two or more forms, actually two forms, of an element this time in the same physical state. Now, based on that, are diamond and graphite polymorphs of carbon? Yes. But can they also be called allotropes? Yes, because carbon is what now? An element. So when the polymorphism is exhibited by an element, you call it allotropy. See another element that exhibits allotropy, oxygen. Oxygen can exist in the form of dioxygen or in the form of trioxygen. I'm talking about O2 and O3. Of course, O3 is also called ozone. So dioxygen and trioxygen are the allotropes of oxygen. What about tin? tin can exist in the form of gray tin, and white tin. So we have gray tin, we have white tin, although there's a third one called rhombic tin. These are polymorphs of tin, but they can also be called allotropes of tin. What else? We can have allotropy in sulfur. As a matter of fact, there are different elements that exhibit allotropy. Another very popular one after these ones is phosphorus. Phosphorus can have the white, all right, white phosphorus. There's also red phosphorus, and then we have black. Black actually comes from red. So there's white phosphorus, there's red phosphorus. Now for sulfur, what are its allotropes? We have what we call rhombic sulfur, and then we have what we call monoclinic sulfur. So sulfur can exist in these different forms, and they are both in the same state, the solid state. So we say these elements exhibit polymorphism, but more precisely, they exhibit allotropy. Now, there's an interesting difference between the allotropy of carbon and oxygen, as well as phosphorus, and the allotropy of tin and sulfur. Here is the difference. In the case of tin and of sulfur, there is usually something we refer to as a transition temperature. What do we mean by transition temperature? It is a temperature beyond which you have one allotrope and below which you have the other allotrope. So let's say a transition temperature of 50 degrees Celsius exists for a particular set of allotropes. It means below 50 you have that element existing in form of this allotrope. Then above that 50 you have the element existing as the other allotrope. All right, so we say in that case it's a transition temperature. So for tin, for sulfur, there's a transition temperature between their allotropes. But for these two cases, no transition temperature. There's no temperature that separates diamond from graphite, as it were. So that type of allotropy, where there is no transition temperature, such as in carbon, in oxygen, in phosphorus, is referred to as monotropy. And then the second type, where there's a transition temperature, is called enantiotropy. All right. So enantiotropy and monotropy are the two types of allotropy. So that's about allotropy and polymorphism. Thanks for watching.